Hello, everybody. Welcome to our second annual, hopefully final annual, but our second annual online star party. I'm Mary Beth Lachak, Director of Strategic Communication here at the Canada, France, Hawaii Telescope. And I am joined by the always lovely, always wonderful Jamika Marshall. Jamika is with the Gemini Observatory and Noir Lab. She is our telescope person who is at the Maunakea Visitor Information Station at 9,000 feet. I also want to give a shout out to Callie Crowder, who's taking care of the back end logistics of our broadcast tonight. So this is one of those kinds of events that if you want to come and go, we encourage you to stay for the entire time, but understand that, particularly I see we've got some people from Colorado and other places. If it gets late and you want to go to bed, we are recording this and you'll be able to watch it later. So, every year, CFHT, the Canada, France, Hawaii Telescope, hosts a star party after the Waimea Christmas Parade. Last year with COVID, and then this year with this continued social distancing on the Big Islands, we've done it with the assistance of Jamika and our friends at the Visitor Information Station. We've done it virtually. So I'm going to turn it over to Jamika to start off with our first topic. Jamika, what do we want to talk about first tonight?
Aloha! I am so excited to join you today here from the 9,200 foot level, the Visitor Information Station. We have a beautiful evening here, as you can see behind me. And Mary Beth, and maybe we can start out talking about that beautiful glow where the sun was. What is that?
So Jamika, that is zodiacal light. Why don't you fill us a little bit in on what zodiacal light is?
Oh, me. Okay.
Sorry.
Do that. Just a second, let me pull up my notes here. So the zodiacal light, I'm sorry here. First, I'm standing in front of the camera, and what you're seeing people walk across, because first of all, that is our sunset hill, Pu'u Kalapiamoa. So if you see little dots going across, that's what it is. It's not anything strange. And zodiacal light. So let me.
I'll jump in, Jamika. I put you on the spot. That's not fair. So zodiacal light is the light that extends along the zodiac, which is where the phrase zodiacal light comes from. So when we talk about the zodiac, it's, we hear a lot about that when it comes to astrology, but for astronomers, the zodiac is also known as the ecliptic, the path at which the planets, the sun, and the moon all pass along the sky in the earth. And so what we end up seeing, this zodiacal light, it's best seen during twilight, after sunset, in the spring, and before sunrise in the autumn. That's why we just have that faint glow there. What we're actually seeing there is some interplanetary dust that kind of straddles that ecliptic plane, and the light from the sun, is illuminating that. And that's what we're seeing when we see that zodiacal light. Now, right above that light is the planet Venus. Now, we're going to come back and talk more about Venus, but it is the brightest object in the night sky right now. Next to our moon. And it's the third brightest object in the sky, but we're going to save Venus facts until it's time for Venus. So while Jamika's getting set up, I'm going to move on and talk a little bit about our nearest star, which is the sun. And so oftentimes when we think about astronomy, we're not necessarily thinking about the astronomers who study the sun. And so we have here in Hawaii, I'm looking for that page. We have the Daniel K. Inouye Solar Telescope, also known as the Inouye Solar Telescope. Sometimes also referred to as DKIST. And so our friends over at the Solar Telescope, they recently, what we call commissioned their telescope. So they have started doing testing on their telescope. It's located on Haleakala. And so we're going to take a look at the very first image of a sunspot that was taken using this Daniel K. Inouye solar telescope, the Inouye Solar Telescope. And what we see here, and you can see the caption there, this is using their solar wavefront correction context viewer camera. And this is from earlier this year. And so what we see here, this dark spot is a sunspot. Now, sunspots are areas of the sun that are cooler than the rest of the sun, which explains that sort of dark color. There are also areas that have additional magnetic field. So the magnetic field within the sunspot, it tends to loop from sunspot to sunspot. That's why we often see them in pairs. And so what we're seeing here is a really, quite possibly the closest, most kind of in-depth image that we have seen of a sunspot from the Earth at the very least. And so as you see here, it's sculpted by the intense magnetic fields and hot gas boiling up from below. So actually, let's look a little bit more at those hot glass at this sunspot. You can see it's absolutely massive. From this particular image here, you kind of, without the scale, you kind of get the idea that, oh, this is a little blotch on the sun. But we see here, it's actually, the heart of this is roughly the size of the US mainland, about 5,000 kilometers in diameter, I guess in width. What we're seeing here, moving on, you'll notice in our sunspot images, we're seeing these sort of like granulations. And so when we look in here, this is features as small as 18 miles across. So if you can kind of imagine some of these smallest areas, 18 miles across. This is the highest resolution image of the sun that we've ever received. And so when we think of the sun, we often talk about the surface of the sun. But the sun, like every star, is made up of hydrogen, helium, and other gases. So the universe as a whole is made up of about 74% hydrogen, 24% helium, and 2% everything else. Astronomers, the periodic table has hydrogen, helium, and the metals. So while in chemistry and, us who are non-astronomers out there will think that, like oxygen isn't a metal. For astronomers, it is, because it's not hydrogen and helium. And that metallicity is what makes things different, what makes, you can tell a lot about a star by its metallicity. And we'll talk more about that later. But when we think of the surface of the sun, I want you to think of it roiling and boiling, similarly to like the convection currents you would see in hot water boiling. You get these hot bubbles of gas in the, in our water, these hot bubbles in our kettle example, rising to the surface and sort of popping. And so what we're seeing here are those edges, materials rising, and then as they fall, they cool back down. And so those are going to be the darker edges that we see. So Jamika, are we ready, or are we going to keep talking about the sun? Because I can show these Inouye telescope pictures all day.
All right, we can get started.
All right, I will stop my screen share and I will turn it over to Jamika.
Awesome, thank you so much. All right, I am just getting started here. Can I see if I can turn so you all can kind of see the setup here? Okay. It's hard to see my telescope. Okay, so I'm using a 4-inch refractor. It's a Barska, and we can talk about the differences between a refractor, and a reflector in just a moment. But whenever you're going to set up to do viewing, typically need to do an alignment. And I apologize, it is very windy, and I see that you all can see my camera moving. Sorry about that.
Very windy and very cold, it looks like. You're all bundled up there, Jamika. Do you know what the temperature is there now?
Mary Beth, I will pull that temperature up right now. And I'm going to my weather channel app. And right now it's coming up and it says, can you see that? It says
40 degrees.
But feels like 33. And it really does. So you all are nice and warm here, while I am happy to be up here sharing the stars with you. All right, so whenever I'm trying to get set up, want to start with an alignment. Now, doing a 2 or 3 star alignment allows your telescope to know where it is. Now, of course, that's assuming you're using a telescope with a go-to function. If you're using a manual telescope, like my favorite Dobsonians, I love Dobsonians because they allow you to learn the night sky by moving it on your own. So for go-to telescopes, you can run it manually as well, but to use the go-to function, you want to start with a 2 or 3 star alignment. Now, you can see behind me, Venus, and I can do the camera a little bit. We have a few stars coming out, and in about 10 more minutes, we'll have a lot more. Now, the moon is out, which we're going to look at later, but the moon washes things out. So to get my telescope set up, I am going to do a 3 star alignment, one in the east, one in the west, and maybe one in the south. But of course, it needs to be a little bit brighter to do that. Once I have my alignment done, then I will be able to then go to my object without having to correct. Because if I don't compensate Earth, that's how it's tracking against the star alignment. So, Mary Beth, 10 minutes, I'll have enough stars to be able to do a 3 star alignment. But I take it that is not how the CFHT telescope works. Do you have to do a star alignment before you all get started?
We do not, Jamika. We do not have to do a 3 star alignment. Now, we have 5 cameras. And so when we take our images at the beginning of a night, particularly if we put a new camera on, we run a couple of focus sequences. Every so often, we do have to run a pointing model, which is sort of similar to that. And we'll check our pointing, but we have a model that allows us, and like I said, we check that every so often. We have a model that allows us to kind of calculate for that. However, when we're using, like, say, the instrument that's on the telescope tonight, the telescope doesn't get us exactly to where the star is. We end up with a finder window, we call it our guider window, that pops up, and the remote observer has to manually select the star from a finding chart. So let me actually bring up a picture here of what the inside of our telescope looks like. And you can see that you'll see that there is a little bit of a difference between the Canada, France, Hawaii telescope and the telescope that Jamika is using. So here we are. This is us, the Canada, France, Hawaii telescope. We had our first light in 1979. And so we're what's called an equatorial mount telescope. You'll notice it is actually yellow and brown. So this is our horseshoe, and this is the yoke of the telescope. Right here, you can kind of see where my cursor is. That's where our primary mirror is. It's a 3.6 meter primary mirror. Now, we have the option to either put a camera at the top or one at the bottom here. In this image, our instrument CTEL is sitting at the bottom of the telescope. So the light from space comes in through our shutter. It reflects off of our primary mirror. It bounces back up to our secondary mirror and then comes back down through a hole in our primary to the instrument at the bottom, which we call Cassegrain. We can also, as I mentioned, put a camera at the top of the telescope. So light from space comes in, reflects up, and hits what we refer to as prime focus. So you can see there's a little bit of a difference there. We are recording all of our images on a digital camera. And so regardless of the instrument that's being used, there's some sort of digital camera that records those images. We specialize in wide field astronomy, meaning we take giant pictures of the sky. MegaCam, our workhorse instrument, actually takes pictures about 4 full moons, the size of like that block on the sky. And WeirCam, our infrared camera, is roughly about 1/4 of that size. Now, the telescope that Jamaica works at, the Gemini Observatory, is our neighbor on the summit. Gemini is an 8-meter mirror, so that is a larger mirror size. And so what might take an hour at CFHT, at Gemini may only take, let's say, 10 minutes because their collecting area is so much larger than ours at CFHT. So we don't try to compete with Gemini. We do science that is very specialized and ends up complementing the work that's done at other facilities. You know, one of my kind of favorite examples of how all of these telescopes on the summit work together, on Mauna Kea can work together, is at CFHT, we often work with the Pan-STARRS telescope on Haleakala on Maui. So Pan-STARRS is scanning the sky on a regular basis, taking images, and astronomers at the University of Hawaii Institute for Astronomy, they have a whole group that are looking for asteroids and comets. So they might discover an object that they think is a comet, or an asteroid. They'll be able to tell because it's moving differently. As the Earth rotates, it rotates at the exact same rate, so stars in the sky move across the sky at the same rate. Doesn't matter if the star is Sirius, one of our closest neighbors, or if it is a more distant star in our Milky Way, the rate is roughly the same to your naked eye. Planets move differently. That's how we can see them in the sky and how they were initially, we see them in the sky because they are reflect sunlight back at us. But ancient peoples realized that these objects, these planets, which are going to be some of the first things that we talk about, that they move differently. They move a lot faster because they're a lot closer to us than the more distant stars. Similarly, with an asteroid, or a comet, if you're taking a picture of the sky like Pan-STARRS does, from image to image, you're going to see this little dot move a lot faster across the sky. Now, to get a good orbit, you need to know exactly where that object is multiple nights. So one night, you can't tell if that comet is going to be moving towards you, diagonally. And so they'll come to CFHT and use MegaCam to have a really wide area so that if they're a little bit off on the orbit of that comet or asteroid, they will be able to recover it. Now, let's say that asteroid looks a little bit brighter than what they were expecting. They might use a telescope like Jamaica's Gemini Observatory, the Keck Observatory, Subaru Observatory, to take a spectrum, to take a rainbow of the light from that asteroid, break it down into its component colors, and determine more about the composition of that asteroid. So that's one way that our telescopes work together. Another is, and this is actually really, really cool. We have an instrument at CFHT called Espérance. It's a spectrograph. So it takes the light from one star, again, breaks it down into a component rainbow. And from there, when we're not using it, we have a fiber optic cable that connects Gemini and CFHT. And the team at Gemini can actually use our instrument, their mirror, our camera, in 2 separate buildings. So Jamaica, where are we at in your setup process there?
All right, Mary Beth. Okay, so now we have pretty much all the stars out that I would need to start my alignment. But before I start my alignment, I would like to talk about Venus. And Mary Beth, let me know if you can you see my laser pointer?
We can see Venus. If not, yeah,
Okay.
it's the bright thing in her object, guys, in her picture. If you can see it and it's glowing, it's Venus over Jamaica's shoulder there.
This is Venus. Now, this is super low on the horizon, and by the time I do my alignment, it is going to be gone. But Mary Beth is going to talk to us a little bit about Venus and talk about something interesting, which is that it goes through phases And why is Venus so bright? Mary Beth.
So Venus is often called Earth's sister planet. And I like to, here's my stuffed Venus. Venus is not a girl. Venus was named after the Roman goddess of love and beauty, Venus. And that's because it's so shiny, it's so sparkly, so brilliant from the Earth. The reason for that brilliance is what makes it, in my mind, a little bit more towards the Earth's kind of wicked stepsister to a certain point. Venus has a really high, what we call albedo reflection. A lot of the sunlight that shines on it is reflected back. And that is because Venus has an incredibly thick cloud layer. So being on the surface of Venus, and I'll tell you more about these clouds in a minute, being on the surface of Venus, the pressure, the atmospheric pressure from the atmosphere is similar to being about a mile under the ocean here on Earth. You can imagine all of that pressure. Then the atmosphere on Venus is full of hydrochloric acid. So it rains acid on Venus. These thick clouds full of hydrochloric acid and sulfuric acid, they also make the planet very warm. So being on the surface of Venus would be like putting your hand in a pizza oven, having it run over by a school bus, and having acid fall down on it all at the same time. Now, about a year, maybe a little over a year ago, there was an announcement that some astronomers found evidence of phosphine in the atmosphere of the planet Venus. This is something that's being watched very carefully because phosphine is what we would call a biomarker. Biomarker doesn't mean it's life, but it's one of the things, one of the elements, the compounds that astronomers might look for in their search for life. And so phosphine can be given off in geological processes naturally. It can also be given off by living things. Penguins, for example, give off a lot of phosphine in their penguin poop. So it has a very characteristic smell, I've been told, by people that I know that have smelled penguin poop closer than I have. So the team didn't say that they found life on Venus. This team was led by Dr. Jane Graves out of the United Kingdom. But what they said was they found the potential. And so I saw today, actually, that a new mission is going to be going to Venus soon as part of this sort of more rapid, faster, quicker turnaround mission. It's going to be going to Venus to look for evidence of life there. Now, not every civilization called Venus, named Venus after a woman. In Hawaiian, Venus is Hokuloa. In the Mayan culture, it is named after Kukulkan, the feathered serpent god of war. And so with those fun facts, I know that Jamika is slewing to our first alignment star. Jamika, do you want to talk us a little bit more about that process, please?
Absolutely, I'd be happy to.
How many of you in the chat? I'm going to interrupt real quick and do a quick poll. In the chat, please let us know if you have a telescope and what kind of telescope you have. And please feel free to ask any questions to either Jamika or myself. All right, take it away, Jamika.
Awesome. Thank you, Mary Beth. Yes, so I'm going to start my 3-star alignment. And when you're going through your setup, it's going to ask.
My job is to make.
Sorry.
Yeah, all good. Typically ask, do you want to do 2 or 3-star alignment? Now, on a clear night that's amazing, maybe a 2-star alignment is okay. That'll get it done. But with it being super bright outside, y'all, the moon is literally right above me. It's washed out a lot of things. So having a 3-star alignment gives my telescope the opportunity to make sure it's dialed into the right spot. So that when I say, all right, I want to hit go to insert object, it does that with very little correction that I need. So I'm going to my first star, and that is okay. So I'm just entering here, and most telescopes, I think, give a warning to not
Sorry, what was that, Jamika? It's very windy.
Oh, it is. I'm
You
sorry.
know that though.
Like a setup when you're just getting your telescope going before you even get to the 3 or 2 star alignment, that important message to never look at the sun directly. I think every go-to telescope has that.
Yes. Never look at the sun, guys, ever.
Not
With a
directly.
telescope without the proper solar filter. Or just
Exactly.
don't stare at the sun.
Exactly. So I just went past that. Now it's asking me, do I want to choose an alignment star? So I'm gonna say yes. And let me go ahead and say yes, and then I will tell you what star that's gonna be.
All right. Now, when you're picking your alignment stars, Jamika, you're going to want to pick a star that's pretty bright, right? We're not going for the really faint ones, are we?
That's right. I'm not going to go for a faint star because I need something bright that I can definitely see myself to be sure that that's the right star that I'm telling my telescope to go to.
And this is when it's really helpful to have, at least some understanding of stars if you're using a go-to telescope. For example, let's say that you've asked it to go to the star Beetlejuice, which is a really large red giant. It should look a little red in the telescope. If you end up looking at a blue star, you are not at Beetlejuice. And so when you're using a telescope, having some sort of knowledge of astronomy, it seems obvious, but oftentimes amateur astronomers, a professional astronomer might not know every constellation in the sky, might not be able to point out and say, that star. Amateur astronomers tend to be a lot better with that. Now, I'm not saying that for all professional astronomers. I'm just saying in some cases, I played a very awkward game of Trivial Pursuit once where they didn't know what cluster the Hyades was in, like what constellation the Hyades was in. It was a professional astronomer. Got real uncomfortable real quick, guys. So what star are we going to?
All right, so so it gives you suggestions. So the first star it suggested to me was Capella, and Capella is rising in the east over here. And this is in Auriga, the Charioteer, the constellation Auriga, the Charioteer. Now, Auriga is also Hokule. Auriga is also Hokule in Orion. Am I correct, Mary Beth?
I believe so. And it would be called that because while I don't think it looks like a charioteer, it does look like a lay of stars. And for those of you not in Hawaii, Hoku means star. And lei is, the traditional flower necklace, so to speak. And much more beautiful than most. I actually I saw some beautiful leis the other day. So it looks like basically a ring of stars. And so not only is this star known as Capella, it's also known as Alpha Aurigae. You're going to have to forgive my pronunciation. I'm not great when we throw in the AE at the end of that one. And what that means is it's the brightest star in that constellation. And so if you were, say, going to send your telescope there, let's say you're a professional CFHT, if we were going to go to Capella, in our catalog, it wouldn't necessarily say Capella. It would probably have its it would definitely have its coordinates. So that is a right ascension and declination, which I like to think as very similar to like a latitude and a longitude on the sky. And so that's going to tell the astronomer, the telescope at CFHT, exactly where to go. And those coordinates are also really, really, really important. And for the amateur telescope, the smaller one that Jamika has. And that's basically what she's doing now. She's testing those coordinates, making sure that when we go to fainter objects later down the line, that it knows that the telescope is going where it's supposed to be.
Exactly, Mary Beth. Now, if I can jump in here, one of the things that, as Mary Beth was saying, it really is helpful to have some astronomy knowledge, or books that you can look at, astronomy atlas of the night sky, and we're going to look at an software program, Stellarium, that you can use on your phone. there's also a desktop version so that you can find constellations and stars. Now, the first star capella was really low, Mary Beth. So it's where I am, you all. There's a building to my right, the Visitor Information Station, but can't see it. So while Mary Beth was talking, I scrolled through 4 or 5 more stars, and the one that is actually that I can go to is called Mira, M-I-R-A, but Mira is right next to the moon, and I cannot see it, even though it's a magnitude, so this looks like magnitude 4. And so this is one of the things that you have to learn to be patient with as you're getting your setup going. Yeah, so Mira is, and we can talk about magnitudes, magnitude 4.9. And normally on a night without the moon, it's a moonless night or maybe, I'd be able to see Mira, but right now it is completely washed out. So I'm actually going to go one more time and see what the next option is.
So Mira, while you're doing that, I'm also going to say Mira is known as Omicron Ceti. And so we're all now very familiar with the word with Omicron in our Greek alphabet. And so this is in the constellation of Cetius, which is actually kind of right next to Pisces and Aries, if you're familiar with that area in the sky. So like Jamika mentioned, magnitude is how bright a star is. Now, magnitudes start at 0. So a 0 magnitude star is going to be a very bright star. I believe Vega is sort of our base 0 magnitude star. As the numbers get bigger, the object gets fainter. And so every telescope has, a limiting magnitude, or a camera might have a limiting magnitude that they can observe with. So if we're observing with Espérance that I mentioned before, Espérance doesn't really, because it's collecting that light from one star, we're kind of limited to magnitude 14th, 15th, which is faint. You cannot see that at all with your naked eye. The instrument that we have on the telescope tonight is called Spiru. Now, Spiru is also a spectrograph. It's an infrared spectrograph. And so an object might have, will have a different magnitude in different colors. So an object like, Mira gives off most of its light in the visible light that our eyeballs can see. It gives off most of its light in the optical light that our eyes can see. A fainter star, maybe an M star or a brown dwarf, if you've heard of them, they might give off a lot of their light, sort of the peak of their light in the infrared, the sort of thermal energy. These are objects that might be the temperature on the surface of a really hot grill or a pizza oven. And so if you're looking at an object in the infrared, you need to know what is the infrared magnitude, not the magnitude in the optical, because it's an object that your eyes might not be able to see in one wavelength, but will be very bright in another. And that's a reason that astronomers need a wide variety of telescopes and instruments, is to look at the entire electromagnetic spectrum from gamma rays all the way to radio waves. It's all light. It's just different colors of light. And so the observatories on the summit of Mauna Kea, they go from the near ultraviolet. So that's because our atmosphere protects us from the far ultraviolet, the gamma rays, and the X-rays. Very good for us, through the radio. And so every wavelength that we look at of light tells us something different about an object. Objects that are visible in the radio or the microwave may not even be visible in the infrared or the optical. And it gives us a different perspective on the universe, which helps us to understand it better. All right, Jamika, how are we coming? Did we luck out with our 4th star there?
All right, so I've still been going through the list of stars, and I've settled on Alpha. So,
which one?
This is Alpha.
Okay.
Yes, and we'll pull it up here. And so this is HR 7444. This is a star. It's over in Cygnus, actually. And in fact, we can maybe talk about asterisms because the summer triangle, even though this is December, right in the west, we actually have the summer triangle. And so that is where the star is I'm going to use for my first alignment star. The summer triangle, the three main stars that make up the summer triangle are bright enough to see even with this moon. And so the star that I'm going to use for my first alignment is right over there by Alpheratz. I'm sorry, right by the summer triangle. And while I'm going to that first star, Marybeth, I think we were going to show them some nice images of Venus before it goes down from CFHT.
I was, yes. And so I've mentioned a couple times that we have the ability to take a spectrum, a rainbow of a star. And so that's something that we've done with Venus on 2 occasions. And the reason that we were doing this is to actually measure the winds of the clouds of Venus. So let me screen share. So the first thing I'm going to show you is our instrument guider. So when we're observing with Esperance or Spiru, because we're going to see a guider image from Spiru here in a little bit. When we're using this guider, as I mentioned, if we're looking to find an individual star, it might, the observer will have like a finding chart. It might look like, oh, it's a cross pattern and it's the one off to the right. When we're observing a planet, the entire planet in some cases can fit in our guider window. And so this is the case here with Venus. So here we have Venus. It's at, as Jamika mentioned, a phase. As Venus orbits the sun, much like as the moon orbits the Earth, different amounts of the planet are illuminated by the sunshine, and we see different phases for it. And so here we'll notice that we see not a full Venus, this is a phase of Venus. And when the astronomers who were taking these observations wanted to get in detail, they needed to figure out exactly where they were going. So they created this map because, as you notice, Venus is featureless. It's not like we can say, oh, even on the moon, like, all right, we're going to go to that crater and then move over a little bit. There's no features because of the uniformity of the clouds on Venus. So they physically taped this grid onto our computer screen, and they would put the area that you see here with the cross, that is the area of light that is going into the telescope and being, the spectrum is actually being taken up. And so what they did with this with these observations was they discovered that Venus has equatorial winds very similar to the Earth. So here in Hawaii, we love our trades, and they essentially discovered trade winds on Venus as well. And so these observations were taken at CFHT. They were taken then again in the infrared at the NASA Infrared Telescope Facility, IRTF, on the summit of Mauna Kea. And they were also using a European Space Agency probe that was orbiting the planet Venus. So I'm going to stop sharing this here. And Jamika, I see that you're slewing there to our star. Have we reached it
yet? It is still slewing. We're going back to our second star, and I ended up choosing. Hey, yeah. All right, I did actually, for the second star, go back to Capella, because it is over here in the east. So Alpheratz was over in the west, and I think I said you want to choose stars in different areas of the sky.
Yeah.
So even though Capella is not ideal, I do see where it is because I know Hubble, Origa. And so that is what I'm doing now. Just slewed to it. I'm going to lock that in and then do my third star. And I will be back with you once I have that third star locked in, and then we'll be ready to start our tour with the moon.
Excellent. So we're going to be, as Jamika mentioned, we're going to be starting with the moon. And so I want to show you a picture that was taken oh, wow, it was decades ago now at this point. I just realized that was taken with the Canada-France Hawaii telescope with our old our older camera 12K. So it was a third of the size of our current megacam. And this is an image that we took of the moon using 12K, probably, I'm going to say about 20 years ago. And what we see here are these craters and flat areas there. If you want to think of the moon, when we think of the Earth in terms of geology, we have, a crust. I like to think of the Earth as a bit like a peach. You've got that thin skin that's a crust. You've got that juicy interior that's a mantle. We see that as lava. And then you've got a core in the center, and you actually have an inner core and an outer core. The moon is no longer geologically active, so it's a lot more like a Tootsie Pop. So you've got the candy outside, Tootsie Roll inside, that is the core. We can tell that's not always the case on the moon by looking at its surface geology. We see these here craters. These are areas where the moon was impacted by an asteroid at some point in its development. The Earth also gets hit. We see Meteor Crater and other, notable craters around the Earth. But many of the smaller impacts are worn away by erosion. The moon doesn't have wind and water and plate tectonics like we have here on Earth, so we see no erosion there. Those astronaut footprints are in the exact same spot as they were in 1969, when Neil Armstrong and Buzz Aldrin first stepped on the moon. So what we can tell, though, is inside this crater, at some point, it filled in, giving us an indication of geological activity. So we don't have a deep hole here. We have this filled in area. So what's possible is impact that created a lava lake, and we have a ring here. We also see, since that geological activity occurred, that this portion of the moon has been impacted again. We see new craters that have not filled in. When we look at some of these areas, we see what looks like a little bit of almost like a peak in the middle. And that's the characteristic shape of an impact crater. If you see an impact craters have a ridge around the outside at the edge of the craters, and then they have a peaking in the center. And so that's a very obvious to geologists when they see something like this, that it in fact has an impact crater. Now, I run a program called Mauna Kea Scholars, where Hawaii public high school students can apply for observing time on the Mauna Kea observatories for their own independent research. And one of the very first projects that we had in our second year from a student at Kalani High School, what he actually wanted to do was take measurements, take spectrum using espidons of the inside of a crater, and then the area surrounding a crater to see what the difference in composition would be, what minerals might have been brought up in the eruption and then subsequent filling in with the moon magma, and how might that differ from the surrounding crust area. So that was a project that he worked on. And how are we doing over there, Jamika? Or am I talking about the moon a little bit more?
Sorry, yeah. So I just finished my third star, and I actually ended up being back over in the west with Altair, back over actually in the summer triangle, which is low in the west. The 3 stars that make up the corners. Vega, of course, super low as part of Lyra. Then you have Altair, which is what I just used, and then Deneb, which is part of Cygnus. So now that I have done my alignment, we are ready to go to our first object. Of course, is going to be the moon. Now, it is really interesting about the moon, and maybe a few things. One, the moon is actually getting, over a period of time, slowly getting further away from us, and maybe Mary Beth can talk about that. And then also, when is the best time to look at the moon? We can see shadows in the craters and things like that. Yeah. And I'm going to be pulling up my image here. It's switching to on screen the telescope camera. And I think hopefully we can chat about the most recent lunar eclipse as well too. And we, an IFA astronomer, Roy Gal, did an awesome live stream of that. So I will be switching over to that camera while Mary Beth chats about those, and I will drop a note in the chat, Mary Beth, when I'm ready to switch to the telescope cam.
All right. So Jamika mentioned a lot of really good things there. So I'm going to start off with the idea of a lunar eclipse. And so a lunar eclipse occurs, and I thought to myself, like, oh, I don't have my stuffed planets to do a lunar eclipse, but I'm pretty sure on my computer here, I have my, yes. All right. So when we have a lunar eclipse, and our most recent lunar eclipse occurred last month. So, all right. So in a lunar eclipse, the Earth, the moon, and the sun are all in a straight line. And so the Earth orbits the sun, the Earth goes around the sun, and that takes 365.25 days. And the moon orbits the Earth. And because the moon moves around the Earth, that's why we have phases. And so the phases of the moon take roughly 1 month to go through an entire phase. That's actually where the word month comes from. Now, you would expect to see a lunar eclipse when the moon passes through the Earth's shadow, or a solar eclipse when the sun passes, when the moon is directly between the Earth and the sun. You would expect for that to occur every month. And that would be the case if the moon's orbit was a perfect plane, was straight in the same plane as the ecliptic. It's actually tilted about 5 degrees, and this is more than 5 degrees. I'm doing this for emphasis, which means that we actually end up with 2 nodes. And those 2 points, if we imagine that this is, turn it this way now, we end up with 2 points where the moon's orbit intersects with the ecliptic path of the sun across the sky. And so we have a lunar eclipse when the moon is at full and on a node. We have a solar eclipse when the moon is at its new phase and on a node. And so one would expect that during a lunar eclipse, we wouldn't see the moon at all, but that's not the case because of the Earth's atmosphere. So the Earth's atmosphere refracts the sunlight shining on the Earth, refracts that sunlight onto the moon's surface, which is why the moon turns a pinkish or a red during a lunar eclipse. Now, these are frequently called blood moons. It's actually something I'm gonna go on a soapbox, which is host's prerogative. I don't love the phrase blood moon because it sets up an expectation that the moon is going to look blood red. How red the moon looks really depends on the particulate count of the Earth's atmosphere, how much ick is in the atmosphere. I'm on the Big Island. I saw an absolutely beautiful red sunset tonight with a fiery red moon because of the fog, additional particulate ick in the Earth's atmosphere. If the moon, we don't have a whole bunch of volcanoes erupting, the moon might just look maybe a little bit orange or a little bit washed out. And as I tell students, you go outside expecting a blood red moon. It's not. You decide astronomy's stupid. You go in your house and you're done forever. And we've lost you because there was a cute name. It also means that when I talk about lunar eclipses, I'll ask, a fourth grader, how many of you have seen a lunar eclipse? And none of them will raise their hand, but one will be like, I saw a blood moon. And, they're the exact same thing, but because one phrase is much more popular than the other, the student doesn't actually make that connection initially. And I know that happens to some adults as well. Now, I'm going to stop this share and we will put the link in the chat to Dr. Roy Gal's live broadcast from his driveway of the November lunar eclipse. Jamika, are we at the moon yet?
Okay, so I turned my camera, and I have lots of wind happening here. people are trying to help me with things blowing. Thank you. Okay, so hopefully you can see me. Can you still see me, Mary Beth?
We still see you, Jamika.
Okay, so I am slewing now to the moon. Now I am actually looking through my eyepiece right now to go to the moon. Now that I've done my 3-star alignment, I now have to make sure that my finder scope, I'm using a Telrad, is also aligned so that when I look through my finder scope at the moon, for example, it's actually going to appear in the eyepiece. So I'm going to slew right now to the moon, and I'm going to make sure that it's in my Telrad. Now, Mary Beth, I'm sure on large telescopes, well, actually, I don't know. Do you have a smaller telescope that you use as a finder scope on your large instrument?
It is such actually a funny question that you ask, because we're in the process of making one. So no, we typically don't have a large telescope that's used as a finder scope. However, we are working on an astrometric camera, which is exactly that. It's going to be a small telescope. It is a small telescope mounted to the side of our larger telescope that we'll be able to use as a finding scope. Again, when we're looking at those really wide fields of view, it doesn't matter if we lose a star or two on the edges, no big deal. If you're the astronomer using Megacam, you're putting your target towards the center. With those spectrographs, Espérance and Spirou that's on tonight, you want a higher level of precision. And so we will be using our astrometric camera starting probably, well, definitely not this year. It just dawned on me that it is mid-December. Definitely not, excuse me, drinking sparkling water. Definitely not this year, but I would expect, the beginning into early next year that we will start to use that astrometric camera.
Awesome. Okay, so you probably just kind of saw me appear from the ground. That is because thank you. And that is because the moon is directly overhead. That is at the zenith of the sky. That means my telescope has to point directly up. And for me to look into my telescope looking directly up, I have to get underneath it on my knees to look up through it. So that's what I was just doing.
We appreciate your dedication. And yes, Ray, it is breezy and she is staying warm. Thanks, Ray, for tuning in. Ray was with us last year when we did this for the first time. Ray was the previous manager of the Visitor Information Station, who is now relocated to the mainland. So I am so excited to see you tuned in here, Ray. And thank you for pioneering this with us last year.
Yes,
and hopefully it's the same Ray. Give us a thumbs up if it's the same Ray. Oh. If not, I said lovely words about you and you weren't here to hear them. So anyway, sorry, Jamika, go ahead.
No, all good, all good. Ray was so helpful last time. I know this is a different Ray, but I'm going to back up that shout out to her because it was amazing and I really had a good experience because we dealt with lots of challenges successfully, and I'm really happy about that. Okay, so now my telescope is set up. We're looking at the moon now, and my Telrad is perfect. That's my finder scope. Now I'm ready to take my eyepiece out, right? Because that's what we use. We use our eyepieces to look at through our telescope. And of course, there's lots of different kinds of eyepieces that you can use. For right now, I was using a wide field of view just to find the moon, get it there, make sure I get it centered in my Telrad so that when I take my eyepiece out, and this is it's a learning curve. You take your eyepiece out and then you put the camera in. And what I have found is that this camera has kind of a loose cord. So let me first talk about the camera. And then maybe also Mary Beth can talk about CCD cameras on a larger scale on telescopes, on professional telescopes. But let me just point out what I am using here. All right. Okay, I just looked down because something just, the wind just blew it down, but that is okay, y'all. All right, so I'm using this ZWO ASI. This is a planetary imager. Now, I am using this from the VIS. This is the VIS camera. And earlier today, we were working on several different cameras to see which ones would work, especially with the wind, because it's just blowing around so much. My CCD camera was okay, but it was super blurry. So we tried this setup, and this is fantastic. So I will, yeah, there it is, ZWO ASI Planetary Imaging Camera. All right, so this is a CCD camera, as I said, and this one is it's under $400, and it's pretty compatible with most computer systems. Now, there's lots of information on the website about how to use this, and I will say it's mostly plug and play. So if you are thinking about getting yourself or someone else a telescope or a camera that they can use with their telescope, this ZWO one is pretty good. Now, Mary Beth, while I switch out from my eyepiece to the camera, could you talk a little bit about what a CCD is, first of all, and then how we use them and how it's used at CFHT CCD cameras?
Yeah, so a CCD is known as a charged coupling device, CCD, and it is essentially the technology in your cell phone is a CCD. And so CCDs came about by, a need by astronomers and, to be honest, like the military industrial complex, but to be able to take pictures of things. So Galileo, you'll see his notebooks, it's a sketch, it's a pen and a paper. That basically eliminates non-artistic people from being an astronomer, but it also makes it hard to get the really fine details. So from there, they moved to photographic plates, which was a physical piece of glass dipped in a photo emulsion. That photographic plate was then put in the light path, and as light from space hit it, it interacted with the photons. The light interacted with that photo emulsion and created an image. It was then taken to a dark room and developed, and that's when you would see the astronomical image. Now, at the Canada-France-Hawaii Telescope, we work with astronomers from Canada, France, and the University of Hawaii. So imagine if you flew from Paris, you had a week-long observing run, and then you, say, ran over your box of plates with a car because you were tired. That is a true story. So we can see what the flaws are in glass. And so they started making these charged coupling devices. And the way that they work is really similar to a bucket brigade. So we're going to start off with the idea of a pixel. A pixel is I like to picture it in my brain as a little bucket of light, a little bucket that light can fall into. So when we look at megacam, it's a 340 megapixel. So that means it has 340 million pixels as part of this camera. And so we have 40 CCDs, we have 40 amps that are connected to make the detector for megacam. So when we look at a raw megacam image, we actually see lines from where these CCDs are put together. Now, as the light enters the pixel, it makes a count. It interacts with an electron. Now, if you have too many electrons, too much light, your object's really bright, we start to see the kind of a cross pattern that we call saturation. And so a saturated star is going to have what essentially looks like a cross going through the small star there that we would expect to see on the detector. Now that's for optical. If you are in the infrared, you make your CCD out of a completely different material. Now, the UH Institute for Astronomy actually revolutionized the world of infrared CCDs. And one of the detectors are the Hawaii 5RG, the Hawaii 4RG is actually flying on the James Webb Space Telescope when it launches later this year. And at CFHT, we have the next generation Hawaii 4RG, better than JWST, in our instrument Spiru. That's because they had to lock down the detector technology for James Webb before we had to for Spiru. So we were able to kind of wait and get that next model, that next the next latest and greatest Hawaii 4RG. So for those of you living in Hawaii here, as we move closer and closer to that JWST launch, which is currently scheduled sometime around December 22nd, look in the news and on the University of Hawaii's Institute for Astronomy website and social media pages to see more about those contributions that IFA has made to detector technology. All right, so we've passed along the note, as said there, we've passed along the note that Jamaica's with the wind, she's going to be a little more conscious about standing closer. So Jamaica,
oh, okay.
Yes, so Jamaica's getting us ready there.
Okay, I will bring the computer closer to the telescope because I'm actually holding the camera right now. The camera cord is really short, so that's why I was over here because I have it plugged in because it has to go in the eyepiece. So I'm gonna bring so you can actually see the camera here. This is the actual camera, and the CCD tip is right here in the middle. So what I'm gonna do, Mary Beth, is pull the camera, my laptop towards me a little bit. And then I'll go ahead and insert the camera.
Perfect. And just as a note in the chat, Doug, I am not Jamaica's boss, but I will pass that information along to him next time that I talk with him. Doug from Idaho and Wisconsin thinks you need a raise. The kids from Idaho say that, and everybody from Wisconsin agrees. So let me pass that along to Jamaica's boss next time we talk.
Oh my gosh. You're awesome. Oh, and you all, thank you all so much. This is, come on, camera real quick. This is Russell, Loki, and Adrian. Adrian, this is the VIS staff who come around.
Hey, VIS staff.
Yes, this is the VIS staff. They are heading down, but Russell, Adrian, and Loki have been supporting me absolutely all day. So thank you so much. Have a safe drive down.
Drive safe, guys. And with that, it makes me realize that we should give a massive mahalo to Rodrigo Romo, who is the Visitor Information Station manager, and his boss, Stuart Hunter, who is the director of Maunakea Support Services, and the entire Center for Maunakea Stewardship for allowing us to hijack the Visitor Information Station for an evening and do this live broadcast.
Absolutely. You can hear the VIS staff here very happy to have us here and to host us. So thank you. Yes, they are happy for us to do another event like this virtually again. So thank you all so much. Drive safely down. All right. Absolutely. Thank you all.
And I'll be here a little while longer.
Okay. Thank you, Adrian. I appreciate that. Thanks, Russell. All right, so as you can see, there's this tube on the end of the camera that inserts right into your eyepiece, right? And I have one that I can show you there. Okay, so so this is the O-ring. I pulled it out of the telescope, but your camera just sits right there. And it's gonna go right in there. So that's what I'm gonna do right now. I already have another ring right here on my telescope. So now I'm just gonna add this into the telescope. So as you can see, if you could just see me, I was just checking to make sure I'm still aligned in the right spot, and it looks like I am. So this is a good time to go ahead and put this in.
And I will just note that at CFHT on a nightly basis, we do not have to screw anything into the back of our telescope like Jamaica does. We change our instrument every couple of weeks. It involves a lot of people, our operations group staff, our instrumentation group, occasionally our remote observers, and a giant crane.
Okay, oh, sorry. Okay, so now I've taken out the eyepiece and I have put the ZWO camera right there and where the eyepiece was. All right, so I'm just gonna mute myself as I get the camera online. So here, before I share that screen, actually, let me just share. I guess I can share the screen. You can see the screen. So this is my control screen here. Lots of information here on the screen. So I'm just going to pull this up. Now there's two things here. Let me see if I can share. Okay. Let me see if I can share my screen really quickly. Mary Beth, are you seeing my screen with controllers? With the controllers?
Yes, I am.
Awesome. Okay, so close my chat. All right, so there are two kind of settings here, and one is stack. Now, I'm not going to use stack, but I'd like to talk about what stack is. And the other is just going to be a single frame. I'm going to use the single frame. But Mary Beth, could you talk about what stacking is while I am trying to get the moon on screen?
Yeah, so when we want to stack an image, that means that so let's just start with, let's get the elephant out of the room. Astronomers are fundamentally uncreative at naming things. So when we stack images, we put one image on top of another image. Why might we want to do that? Or why might we want to stack images or pixels? If we have an object that's not quite bright enough, what we can do is add a bunch of images together, adding that light to be able to make the image brighter on the camera or in the sort of reduced data, something that you all might be seeing with the CCD. And that's one of the advantages of a CCD over naked eye astronomy for an advanced amateur astronomer. Are you going to start off with a CCD? Maybe. You're ambitious and I like it. But it's one of those things where then you have to know more about the data processing and all of those kinds of bits. Stacking an image is going to allow us to see a fainter image better. And that's really, professional astronomers stack images all the time. When you see those beautiful images, say in a 2022 CFHT calendar on sale today, or really, quite frankly, I give a lot away to people on the Big Island. So I make it sound as though we're going to actually sell most of them. Let's be honest. I'm like planning to give away 200 next week or later this week to kids. So anyway, who am I kidding? When you see those images, you get the perception that it's one image, but in actuality, our calendar images are 21. There are 3 different filters, so 3 different colors of light, 7 images each to give, not only the variety of colors, but also to really get those fine details. All right. Okay.
So here I am. So I'm switching here from trying to get out of the stack to single frame here. Yes. And so on the screen here is the showing the camera that we're using, and I am, yes, okay. All right, so let me share screen. Oh no, I went out of the wrong one, sorry. Okay, I'm trying to share this screen. Okay, so now it's detected the camera. The camera kind of got it's a short plug, and I unplugged it by mistake. So that took me a minute to get back down. So now I'm just making some changes, changing the brightness of the image. All right, and so I am going to go back again to the telescope and get the image here now that the camera is plugged back in. Now, I'd imagine though, you don't have to do all this kind of setup back and forth when you and your telescope operators get started in the evening in the control room. What do they have screens? Do they have to troubleshoot things? What is that experience like?
So Callie, who is one of our remote observers, is actually online now. I am not going to put her on the spot by turning her camera on, but Callie, can you send me how many screens you actually have in the control room? When you're in our control room, we've got main screens, and then we've got a weather screen. So we operate remotely from Waimea, which means that when Callie's observing, or like when Lisa's observing tonight, you never go to the telescope. So I started at CFHT. I'm going to do a back in my day. When I started at CFHT 18 years ago, I actually worked at the summit with one other person. Being at the summit of Maunakea at 14,000 feet is roughly like trying to do your job after 2 glasses of wine on an empty stomach. The lack of oxygen, or the less air, so there's not less oxygen, there's less air overall, which means less amount of oxygen, same percentage. You end up with your brain and your body and your eyes not always working great. So for that and many other reasons, our observers work remotely from Waimea. So Callie right now is in the same building as our observer. They have 13 screens that are used nightly. Most of them are status screens, but we have one screen that is our observatory automation project screen. So that allows the observer, Lisa tonight, to control everything remotely. She can operate our shutter remotely. She can turn lights on and off. She can turn our hydraulic systems on. Then we have our observing screens that are used to actually take our observations. So when you are an astronomer at CFHT, let's say that Jamaica was a CFHT user. So we're just going to say that Jamaica is from Canada. So Jamaica works at the University of Victoria in British Columbia, and she's one of those asteroid people. So she wants to look for asteroids. She is not going to fly to CFHT for those observations. Rather, she's going to go online and fill out a detailed online form. And then we have 6 months to take that data for her. This is called queued service observing. So that means that Callie and Lisa and Cam and Helen and Christy, our observing crew, they take all of those observations. So we have a coordinator who looks at the start of the night, or actually in the daytime, and they come up with a whole plan for the night. So a great example of why we do this is our instrument tonight, Spiru. Spiru's mission on this Earth is to look for planets around distant stars, extrasolar planets. Now, when we're looking at them, they're looking to detect the wobble in a star, the wobble in the spectrum, rainbow of a star, back and forth to see if there is a planet. The spectral lines will wiggle just a tiny bit. That is not an observation you make in one day. That is not an observation that you even might make in a week. We have astronomers who look at stars for maybe 1 hour every night for 2 weeks at a time, every month for a year, to make these really, really small observations. Imagine again, you have flown out from Victoria or Paris or Nice to use an hour of telescope time. It's just not super efficient. So that's how we operate. Like I said, most of the screens that we use are status screens. So we have this interface called the observing tool. It takes the information typed into our online form by the astronomer in Paris, and it moves the telescope, it slews the telescope to that exact spot that we want. Callie's finding chart then pops up. She'll look at and try to match the patterns and pick the proper star and start her observations. So all of ours is, much more automated. When we think of the staff in an observatory, probably think mostly astronomers. Roughly a quarter of the CFHT staff are astronomers. Everybody else does everything else. So my job is fundamentally doing exactly what I'm doing right now, explaining astronomy to people. We have computer programmers. All of the software that we use at CFHT is custom built and designed. The software that Jamika is using tonight is something that you can get off the shelf, you download, you connect to your computer, your telescope, and you're good to go. For a 3.6 meter telescope, all of our cameras are unique in the world, which means that all of the software that comes with the cameras are unique. All of the physical hardware is unique as well. Oh, right. It looks like Jamika has a blurry moon there, but I see a moon. Our phase tonight is actually a waxing gibbous.
Yes, yes. Okay, so I've been fumbling. I wouldn't say fumbling. I've been doing some testing of things here on my own in the background while Mary Beth's been talking. And what I need to do, and I'm not going to do this live right now, what I've been messing with is the gain and bend, especially the gain. The moon is so bright, and I need to compensate for that. And here in the histogram, you can actually see it's changing. I'm going to stop my share here for a second. Well, actually, I'll keep it up for a moment. At the bottom, you can see brightness and contrast. So this is something, I think this is really good. I really want to share this. It does take a while to get things sometimes to work properly. Now the moon is super bright, and I had it too dim, I had it way too bright, then I couldn't see any details. So I've been spending 15 minutes trying to do this. And so this happens, but because we're live, I'm going to just share that that's what happens. I'm gonna stop my share now. But that is what happens. And sometimes if you have the time, you can sit here and give it an hour to try to tweak it. We're not gonna do that because it's coming up to 8 o'clock. So, right? But this is Stargazing Live, you guys. That's exactly what happens. You have to take the time to try to get things to work out right. And I just wanted to share what I was doing, and then I was having some issues because this happens. And now, as Mary Beth says, is this a waxing or a waning gibbous?
Waxing, according to my watch. It's a great feature on the Apple Watch, because I do a lot of work with kids, and there's nothing more embarrassing than talking to kids about the phase of the moon and then you don't know what phase it is. So very handy feature in my line of work.
Awesome. So that I'm going to try to come back to the moon later. I don't want to stay too long here, except to really share my experience here. And I have to say, I try to start off with things that are bright so that I can do the alignment quickly with my tail rad once I have my 3-star alignments done, and I have something bright in the camera that I can look at. When you can't see anything, you're not sure if you actually have it. Well, we have part of something, so we know we have it, but it will require us some time working on the gain and bend to get that image just right. So if you'd like, Mary Beth, I'm going to pop off screen and move on to Jupiter, which is our next item. And I'm going to pull up also Stellarium as well, so that we can talk about how to find objects that are not as bright as the moon, the moon is super obvious. But what if I want to find something that's not as bright as the moon? And I know that there are phone apps I can use, but what if I want to use my computer? Well, Stellarium is a fantastic software program that I'm going to bring up in just a moment. Mary Beth, can you start us off with Jupiter while I switch and slew to Jupiter?
Yes, absolutely. So this is Jupiter. Actually not. This is my stuffed planet. Before anybody asks, they are celestial buddies. I get a lot of questions about them. I have the full set. So Jupiter is the largest planet in our solar system. If the solar system, the mass of the solar system, 99.9% of it is in the sun. Of the remaining percentage, most of that, 99% of that, is in the planet Jupiter. Jupiter is a gas giant planet. So when I talked about the Earth versus the moon in terms of geology, and I said the Earth is like a peach, I like to think of Jupiter is not necessarily a peach. It is kind of like a balloon planet. It's made up predominantly of hydrogen and helium. You'll notice that there are stripes here. Those stripes are actually what you would see on the planet. These are bands. So these are winds going in different directions. So this is the wind going in different directions. And the colors that we see from Jupiter come from those metals, that metallicity, the impurities. Usually in the case of Jupiter, that is going to be methane, ammonia. So Jupiter is hydrogen gas, hydrogen and helium gas on the outside. And then as you would fly deeper into the planet, you get liquid hydrogen and liquid helium. And as you go even deeper, you get liquid metallic hydrogen and helium. So this is hydrogen and helium that is so compressed by the immense gravity of the outer layers of the planet that it becomes a metal in that traditional connotation of it, something that can conduct electrons. Now, astronomers believe in the core of Jupiter is a core, like a physical core. Now, you wouldn't be able to stand on it, but it would be maybe roughly the size of the Earth, not physical core, a rocky core, probably roughly the size of the Earth. Now, a lot of students, when their first question about Jupiter is, if it's a gas planet, can I fly right through? And the answer to that is no. As I tell little kids, if you have one feather, it's light. If you have a million feathers, it's heavy. I'll also talk to them with a pillow. You put one pillow on top of your head, you're fine. You put 500 pillows on top of your head, that last pillow is going to be crushed. And so that's essentially what happens with the gases as well. That intense pressure causes a crushing force and puts pressure down on there, which causes that liquid hydrogen, that liquid helium, and makes it impossible to fly through the planet. As you fly through, as you would go deeper and deeper into the planet, the temperature heats up as well. Gas under pressure gets a raise in temperature. So if on not only on Jupiter, but on other gas planets like Saturn as well, if there is a probe that's orbiting, a space probe that's orbiting the planet and perhaps orbiting some of the moons, the flight control team will actually crash the planet into the atmosphere, crash the probe into the atmosphere of the planet so that it is destroyed and the heat ends up decontaminating any microbes that might be from Earth that might be on the outside of that. Now, you'll notice the red nose here. That is, in fact, the great red spot of Jupiter. This is a hurricane. Now, it looks small here, but the great red spot is actually larger than the size of the Earth, and it varies in size. At its largest that we've seen, it's about 40,000 kilometers. Now it's shrinking down to about 16,000 kilometers. And the great red spot was one of the first things that Galileo saw in his telescope when he looked at Jupiter. So we know that this hurricane has been raging continuously since 1609, when Galileo first peered through a telescope. Now, when we talk about Jupiter, we would be remiss to not mention its moons. Jupiter and Saturn constantly go back and forth between, which has the most moons. I'm a bit of a moon snob because any rock that is orbiting Jupiter is going to be a moon. So if my pen started to orbit Jupiter, it becomes a moon. This is not, when we're talking about moons, this is not what we're thinking of. We're not thinking of the moons that are, like a mile or two across. What we're thinking of are the big moons. And so in the case of Jupiter, those would be the 4 Galilean satellites. Io, which is one of the most volcanic places in the solar system. Europa, astronomers believe that there could be underneath the icy crust, a ocean, potentially even a warm ocean, one of of all of the places that have the option of life in the solar system. Europa is a very strong contender for that. There's Callisto, which is one of the most heavily cratered objects of the solar system, and Ganymede, which is the largest moon in the solar system. Now, as I mentioned, Io is one of the most volcanic, and this kind of goes to the question that Jamika had set me up for earlier that I didn't answer because we ran out of time when we were going to move to something else, and that's, why is the moon moving farther away from the Earth? Its answer is similar to why is Io one of the most volcanic places in the solar system, and that's gravity. So as Io orbits Jupiter, when the part of the moon that is closest to Jupiter has additional gravitational pull. So the gravity of Jupiter pulls on one side more than the other, and as it orbits to the opposite side of the moon is being more gravitationally influenced. So we get what's called tidal heating. It's almost like a tug of war that exists within Io. Now, I actually have here an image of Io that was taken by the Keck Observatory for one of those Maunakea Scholars students that I mentioned, public high school students who are using the Maunakea observatories for their own independent research project. So let me bring up the labeled one. So what we can actually see here, what this student wanted to study was the volcanoes on Io and how the composition of what comes out of those volcanoes compares to magma on Earth. So we can see here 4 active volcanoes: Loki, Pele, Marduk, and Cartalagon. Say Cartalagon. Apologies if I have said that crater wrong, that volcano wrong. So on Earth, our magma is made up of rock. On Io, it's going to be made up of ices in the solar system. So basically, think of like slushy windshield wiper fluid combined with, some particles of rock. So Jamika, I see that you have moved back towards the camera. What do you have for us, Jamika?
Yes. Okay. So I was over my slew limit. Jupiter is behind me. And of course, when you set up your telescope, you want your control panel to be facing to the south. And that's what I had. But in trying to pan behind me, right, to see Jupiter, which is right there, I ended up being over the slew limit. Now, over the slew limit means that I have turned either too far left or right for the telescope's comfortability, and it has told me to stop slewing. So you may have seen me do something not great, which was me manually twisting my telescope around there a few minutes ago. I would have taken all the equipment out and then did it, but I was trying to save time and do it that way. So what I have done is move my telescope to now face south where Jupiter is. Now, what I was just about to do is drop into the chat for you, Mary Beth, because you were talking about Jupiter. I would really love to share more about Jupiter and the work that NORLab has been doing with Jupiter, Gemini, with the Juno probe. So I'm going to our YouTube channel right now, and I'm going to grab one of our CosmoView videos And also want to let everyone, if we could play this one.
Absolutely.
Okay, so let me just drop that. I'm going to our YouTube studio. Okay, and all right, so I'm going to drop that in the chat here. All right. Okay. Oh, this is one. Okay, while I pull this up, Mary Beth, I'm going to pop off screen for just a moment while I switch over our YouTube.
All right. I don't have it in the chat yet, Jamika.
Right. Yes, I was at our NORLab Science YouTube, and that was the wrong one. All right, now I'm at the right one here, and here is Jupiter. Yes, this one is amazing. So let me just grab it. All right, copying here, dropping it.
You guys are in for a treat because I have seen this. It is so cool. All right, so let me set this up. I'm going to pause. All right. And start my screen share, and we'll be able to watch this great video that Jamika has provided for us. I'm going to skip the ads so you don't have to watch a YouTube ad. No YouTube, we don't want any of that. I don't want to try YouTube premium free. This is so embarrassing, YouTube. You're embarrassing me. All right. Oops, I am not showing that. Sorry, wrong screen. I shared the wrong screen. All right, so I will put that link in the chat as well. So if you want to go back and watch it later, you're welcome to do so.
Okay, awesome. And I also dropped the press release down there as well too. And now you see I've turned my telescope all the way around, and I have another quick alignment. You'll remember I did a 3-star alignment with my telescope facing the other way. So switching it means that now it's not aligned, and I'm going to have to do it by hand, which is okay. This again is live stargazing, and this is exactly what happens. All right, so I'm going to mute myself, Mary Beth, and let you continue on talking about Jupiter as I get it. And I'm not sure how many people in the audience know, but in the past month, Jupiter has gotten, in November, several impacts. that it took for the inner solar system, preventing those from coming into the inner solar system. There were two objects that impacted Jupiter. I'm going to pause here, mute and slew, and hopefully I'll be back with a nice image.
All right, and I'm actually going to screen share the news release that I just put in the chat, because what I think is so incredible about this is we're looking at, as I mentioned earlier, seeing the universe in different colors of light. So if we go all the way in this direction, we're seeing the optical, and you'll see that this is a Hubble Space Telescope view of Jupiter. This is going to be an incredibly in-depth view of Jupiter. We can see all of those. It almost looks fake, but I promise you it's not. It's Hubble Space Telescope. We can see such exquisite detail there. Now, if we start to slide over here to Gemini, what we're looking at is the infrared. So thermal imaging. I often like to think of the infrared as like night vision goggles for space. What are we seeing that is at that temperature of, several hundreds up to 1,000 degrees? And so Gemini excels at infrared observations. They actually have a coating on their mirror that is a silver coating as opposed to the aluminum at CFHT. And so when we do that, we start to see Jupiter in an entirely new way. The great red spot, which is so prominent in the optical image, completely disappears. You would not call it a red spot if you looked at it initially in the infrared. Similarly, we're starting to see some of these areas here that are much warmer. These are probably rising gases. And this also gives us more information about that banding structure of the planet. So warm air rises, cold air sinks. So what we're looking at here is the warmer stripes, the stripes of warmer air rising up, corresponds with areas, when we look in the optical, that the gas is sinking down. So we're seeing a convection currents along Jupiter bands. And so that's one of the questions that I often get from students is, if there's no land on Jupiter, how's there a hurricane? We see here that the great red spot occurs exactly at the border between two of these warm air rising, cold air falling bands, and that's causing a turbulence. And I bet if we were to scroll over here to this red spot junior, again, not creative with naming, we would see that that's occurring at one of these borders. This is a really interesting feature up here where we're seeing these sort of eddies and swirls that correspond to shadowing here. It kind of makes you wonder, like, what's going on in this area of Jupiter? We have atmospheric gases that we have some cooler areas. So the gas is dropping there, surrounded by these warmer areas. And if we look even more here, we can see this ultraviolet view of Jupiter. So the ultraviolet, it's that same light that causes sunburn. I am very familiar with the impact of ultraviolet light. The areas that we see in the ultraviolet are going to be the areas that either have chemicals that have some sort of ultraviolet sort of reactivity, or areas that tend to be a little bit warmer. And again, we see that here with this stripe here that was our cooler one is, again, very different. This being the coolest part of our whole Jupiter. So I'm going to stop sharing there as we wait for Jamika. While we're waiting, does anybody have any questions? I see a couple people have purchased our calendars. Anybody else have any questions? Anything that you are dying to ask somebody while we wait here for Jamika to get us all finally set up on Jupiter and finish with our alignment and hopefully be able to see the planet? I don't know where the moons are right now. They are something that you can see with the eye, with a telescope. Galileo did, and those were the 4 dots, which led him down his spiraling of the idea of a non-geocentric universe, the idea that the universe does not revolve around the Earth, which was a real big deal back in the day. Also seeing that the planet was spherical. Oh gosh, did I do a whole screen share where all you read is my email? No, okay. What is my favorite astronomical object? Thank you for asking, Jess. So my favorite planet is Uranus. The reason that I like Uranus is for a bunch of reasons. One, it's actually blue. So the same methane and carbon, methane and ammonia that we see in, and other hydrocarbons that we see in Jupiter's atmosphere. I mean, in Jupiter's atmosphere, we see in much greater concentrations on Uranus. It rotates backwards, so it was likely impacted twice during its formation. And so it was likely impacted twice during its formation, turning it on its side. So the North Pole of Uranus is actually where we would expect to see where we would expect to see sort of the equator on Uranus. It also was the first planet discovered. And when I put it in air quotes, was ancient peoples knew about the Mercury, Venus, Earth, obviously Mars, Jupiter, and Saturn from the beginning of people looking up at the sky. Uranus was discovered in 1781 by William Herschel and his sister Carolyn, who gets very little credit but deserves lots and lots of credit. And he actually wanted to name the planet King George III's star because he was the royal astronomer for Britain. And King George III was not particularly popular in the broader European community. He was also at war with France and, the United States, but we didn't exist and no one really cared what our opinion about King George was. He was at war with both Spain and France at that time. So that's when the precedent of naming these objects after continuing to name new planets, newly discovered planets, Uranus, Neptune, and ultimately Pluto after Roman gods and goddesses continued. Well, I guess in these three cases, gods. So Uranus is the father of Saturn, the grandfather of Jupiter. And that's one of the reasons why it's my favorite. I would say my favorite constellation is Orion the Hunter, because it looks exactly like what it's supposed to. And Orion is at the heart of the Hawaiian star line, the Baylor of Makali'i, which is our winter star line right now. All right, so Jamika, how are we doing? Do I need to talk about more favorite astronomical objects?
Well, let me share my screen. Sorry, wrong mouse. Trying to do here. Go into Zoom and share screen. Okay, so you can see Jupiter right here, but I'm again working on the gain and the brightness and the contrast. So of course, the moon was really bright and I tried to compensate for that. Now when we pick up Jupiter, it is not so bright. So let me just share what I've been doing here. And again, you guys, this is live stargazing. So here on the exposures, I lost that. So I'm changing the brightness, changing the contrast, and this is one reason why you may want to do some stacking.
Hey, Jamika, it's hard to hear you again. If you could get a little closer to the microphone.
Yes, I'm so sorry. This
Perfect,
cord,
right there.
The cord is so short, yes. And so what I'm trying to do here is, you see, you have resolution, you have exposure, all of these things need to be changed to bring us a good object here, a good view. So that's what I'm attempting to do in the background, Mary Beth, while you're talking.
All right, so in terms of other favorite astronomical objects, I would have to say, I'm really partial to, I like the Pleiades, the Makali'i. I think that they are, you can't go wrong. They're a beautiful cluster. It's an open cluster. And when we say it's an open cluster, we mean that all of these storms formed at the same time, out of the same cloud of gas and dust. And so they're a perfect little petri dish. When we look up at the Makalii, which is the Hawaiian name for the Pleiades, it is beautiful, and we see 6 or 7 stars depending on how good your eyes are. But it was actually used by a variety of Native American tribes, as it was called an eye test in some cases, how many stars you could see, how good were your eyes. So this is an open cluster. They're very hot blue stars, meaning you can tell a lot about a star by its color. Color equals temperature. So the biggest, the hottest stars are blue. I like to think of them as the kind of like the rock stars of stars. They live fast, they die young, they burn through their fuel at an incredibly fast rate, and they explode cataclysmically and very spectacularly at the end of their life. The stars like the sun is going to be is middle-aged. So where one of the stars in the Pleiades, one of the bright blue stars, like Merope, for example, might live to be 10 million years old, the astronomers anticipate the sun being about 10 billion years old. And we're about roughly halfway through that life, give or take a little bit. And so big stars that are red are stars that are called red supergiants. Again, the creativity in naming. So sticking with the Orion area, Beetlejuice, which is the shoulder of Orion. You can say Beetlejuice, you can say it Betelgeuse. I go Beetlejuice because of the 1980s seminal work of Beetlejuice with Michael Keaton, I think a young Alec Baldwin and a young Gina Davis. Don't know how many times I watched that movie as a kid, but big fan. So for me, it's just Beetlejuice. That is a red supergiant, and it's a really large red star that is approaching the end of its life. Astronomers actually had a bit of I was going to say a scare, but really it was a thrill. About 2 years ago, Beetlejuice started to dim, and they thought that it was approaching sort of the end of its last contraction before a cataclysmic explosion of a supernova. And what ended up happening, there was a lot of questions. So Dr. Steve Mears, from the formerly of the James Clerk Maxwell Observatory on Mauna Kea, he just flew off island today. I don't think you're watching, Steve, but if you are, aloha, Steve. He took a position at Sophia Observatory. Dr. Mears, Steve had a paper that said that he guessed it was not guessed. His data showed that it was actually star spots that might be causing this. So now Jamaica looks like Jupiter. Is that Jupiter, Jamaica?
Yes, I am unmuted already. Okay. Yes, it is. It is Jupiter. And let me give a shout out to Jasmine helping me. She suggested changing the histogram here. There's so many things, so many variables that can change, that need to change in order to try to capture an image really well.
Jamaica, can you come just a little bit closer again to the microphone, please?
Yes. So I'm just trying to get this to not be as bright. And trying to, just troubleshoot. So what I did here was change the histogram settings. This was suggested by Jasmine. Thank you, Jasmine Silva. And also I changed the brightness as well too. So let me just move Jupiter up a little bit and continue doing some tweaking and see if we can get that a little bit dimmer and bring out some moons.
Yeah, so, what Jamaica's doing is in anything in life, a lot of this is science. Some of this is also art. What settings are best to be able to see Jupiter or the moon on any given night, based on the conditions that we have in the sky. If it was a cloudy night, the clouds would act as a natural filter, and we wouldn't even see Jupiter as brightly as we're seeing it right now. Now, you'll notice, coming back to something that I talked about earlier, at the edges of Jupiter, it kind of looks like hair or, like static electricity coming off the edges. It's not actually. What we're seeing there is that saturation in the CCD that I mentioned. Jupiter here is so bright that light is leaking from one pixel, one bucket into the next. And that's why we're seeing sort of that haze that is surrounding it. As someone pointed out there in the chat, yes, Jupiter, Saturn, and Venus are in pretty much one line, that line being the ecliptic, the zodiac, in the evenings in the sky. So I can actually see them really, really nicely off my lanai, Venus being the absolute brightest. And that one to me is farthest to the west, almost a little northwest. Sorry, I'm looking out my window. And then they kind of line up in an arc going across the sky for that. If you're trying to get to figure out exactly where is that ecliptic, look for the moon and then kind of follow in that same arc across the sky. Thank you to Callie for pointing out Ray's question there. Ray's question is, do you think we'll see Beetlejuice supernova in our lifetime? I don't know. So the one point of Ray's question, not the non-flippant part of it, is Beetlejuice is something like 850 light years away, which means we're seeing Beetlejuice as it looked 850 years ago. The speed of light is the speed limit for the universe. It's 186,000 miles per second, 3 times 10 to the 8th meters per second. You can tell which one of those I'm more comfortable rattling off. It is not the miles per hour one. And so when we're looking at the light from Beetlejuice, we see it as it was 800 years ago. Everything in the universe, including our sun, it's a time machine. So we see the sun as it looked 8 minutes ago. So if Beetlejuice supernovaed tomorrow, we on Earth wouldn't know for another 800 and some years. So if by some chance, let's just say that Beetlejuice supernovaed on Christmas in what? Like, I'm just going to use 800 as a round number. I know it's somewhere in there. Let's be honest, like 50, 60 years in the term of an 800-year-old star, 800-year-old light. Anyway, so what it would have had to, basically supernova in like the year 1200 AD, 1221 AD. So I don't know, Ray, it's really hanging on there, but in, 10 billion years of a star, the end of that could be a half a million years. That's, a lot longer than we will ever be alive. So that is sort of, I think, what astronomers are kind of secretly, quietly hoping for, and were secretly, quietly hoping for in 2019 when it was being weird. In addition to the idea of an extra star spots, a cooling on the surface, another hypothesis was that it had actually expelled some material, some gas that created an envelope surrounding it that made the light harder to penetrate, thus looking dustier. All right, so what is that? Mojo, have I ever seen or heard a UFO signal? I have not. So everything I have ever seen in the sky is something that I could explain. One of the most common objects, so if you look at all of the observatories, Canada, France, Hawaii telescope, we are like first in the observatory phone, like in the phone book. If you look astronomical observatories, we're the first. So we get calls from people sometimes wanting to know about UFOs. And while Jamaica's finishing tweaking, I'm going to finish my story. So one of the most common UFO objects ends up being the planet Venus. And as Venus rises in the east over Hilo Bay, through that fog layer, the light is actually broken down and kind of flickers between red and blue, making it look like it's a moving ship. And then as it gets to the top of the fog layer and we have less distortion, it looks like it kind of pops up, making it look like it's had some sort of unique acceleration. When we think about life in the universe, I think so often we think about Baby Yoda or, a Klingon or a Vulcan and kind of forget about the mundane, but more likely life forms. If we look at the Earth, we've got humans and, a handful of other super, intelligent species, octopuses, dolphins, whales, gorillas, all of that kind of stuff. parrots. But we have a lot of grass, we have a lot of plants, we have a lot of insects. And so if there was a planet that was filled with nothing but really intelligent whales that had a massive underwater civilization, i.e. the plot of Star Trek 4, but didn't give off, radio waves or some sort of electromagnetic signal that we could detect, we would not know they existed. Same if there was like alien pond scum or something along those lines. That's what the newly launched or soon to be launched JWST Space Telescope is going to look for, those biomarkers, those signals of how life changes the atmosphere. So, I'm going to take methane, for example. One of the biggest causes of methane in the Earth's atmosphere is in fact cow farts. And so while cows are not, having television shows and putting ultraviolet, infrared or radio signals out into space, they have changed the atmosphere of this planet. And so that kind of thing, oxygen, carbon dioxide, methane, anything that comes, phosphine that comes from a biological process, that is what JWST is going to be looking for in the infrared, and the Mauna Kea observatories and other telescopes currently look for now. So how are we doing, Jamika?
I think I'm unmuted. All right, so I am still trying to get this brightness down. So as you can see, I'm still screen sharing. I changed the exposure. I'm changing the brightness now. And when this refreshes here in a minute, we should see a difference here. So the exposure was 1 second. I changed it to be 0.5. Let me check this. There's a lot of noise in the back, all this noise back here, all this gray stuff. So I'm trying to get rid of that noise while also bringing up a better image. And so what I'm gonna do is see if we can actually just a little bit shorter exposure time here. And try again.
All right, while you do that, Jamika, why don't I talk a little bit about the Geminids meteor shower next week?
Oh yeah, actually, and there were some people here asking about the Geminids earlier. So yes, thank you, please do. And I will continue working on this and shout out for those who are giving me advice in the background. Thank you.
So thank you, everybody who's helping Jamika in any way, shape, or form. So the Geminids meteor shower is going to be, excuse me, my screen thinks it wants to power off. So an asteroid is a rock in space. And I'm not going to go through the entire definition. I will let you watch our video that will be debuting. Callie's going to tell me in the chat when our video will be debuting. I think she was editing it today. Should totally watch it. She put a lot of work into the animations in our new What is an Asteroid Meteorite video. So a meteor shower occurs when rocks from space enter the Earth's atmosphere. As they enter that atmosphere, they heat up due to the friction, the rubbing with the Earth's atmosphere, and they glow. And so they streak across the sky. On any given night, you can go out and lay in the grass and probably see a handful of meteors. During a meteor shower, we're passing through a particularly chunky area of the Earth's orbit. This usually comes from a comet that has melted. So comets are giant dirty snowballs in space. As they orbit the sun, on every pass, they melt a little bit, leaving some rocks and debris across their path, across their orbit. Now, as the Earth crosses that orbit, these smaller rocks these smaller asteroids enter the Earth's atmosphere in larger quantities. So next week, we're going to have the Geminids meteor shower. Because we are a waxing moon, that means the moon is getting brighter, it's not going to be the best time to see the Geminids at the beginning of the week. But the nice thing about meteor showers is, unlike a lunar eclipse, which happens between specific times, a meteor shower lasts like a week or, like a week, 10 days. So if the weather's not great on the day you see the peak, like you see on like the news, like, oh, the peak of the Geminids. Don't worry about it. I also don't like to get bogged down in like, what direction am I looking? They're called the Geminids because they're supposed to look like they are coming out of the constellation Gemini. That's great. If you know your constellations, you know what direction to look. What I recommend is look towards the east, lay down and just kind of look up. Let your eyes get dark adjusted, which means you'll need to be out in the dark for a bit. And just kind of like see what you see. When you start to see the shooting stars, when you start to see these meteors as part of the shower, you're going to want to like turn in that direction and lay back and see even more of them coming over. There are a fair number of meteor showers that occur over the course of the year. I'd say probably the two biggest are going to be the Perseids, which occur in August and are from the remnants of Comet Swift-Tuttle, and the Geminids, which is left behind by an asteroid 3200 Phaeton. Thank you, Callie, for that, for putting which asteroid it was in there. So this asteroid, as it orbits, it just loses pieces. It's falling apart a little bit. This year, we're anticipating about 120 meteors per hour. So this is going to be a good year. And like I said, I really recommend, a little bit later in the week or after the moon has set, going out and trying to take a look and seeing what you can see. Again, I find meteor showers are the one thing that like people stress out a lot about, and it's, you really don't need to. Just go outside, take a drink of some kind, water, tea, something a little harder, apple juice, and lay up and look and see if you see any meteors, any shooting stars. All right, Jamaica is diligently working on Jupiter for us. I think I see a very faint Jupiter there.
Yeah, you do. Of course, it was too bright before, and now we can barely see it. So as you see, I've changed the exposure time, the gain, image, all of these things. These would be different. Your settings for any camera, anything you're going to be using is going to be different for the objects that you use, that you're going to be looking at. So I'm going to try one more time on Jupiter, and I'm going to bring this screen back up. I'm going to move Jupiter back up, and we're going to change our exposure time. Let's see, 0.5, and I'm going to reset that. And let me just move my.
I'm seeing it, Jamaica.
Yes, this is awesome. But you see, it's like such incremental changes, and I have to wait for the refreshing. So I am so excited and appreciate all of you all being here as we do this. Let me, because I turned around on the telescope, so now I'm actually manually having to keep the object in the eyepiece. So let me go ahead and move again, and let's see if we can brighten up Jupiter one more time and see if we can go. All right, here we go.
And so I will just reiterate what I think Callie has put in the chat here. For all of between Callie and I, who you've not met, but believe me, she is here or we would not be operating. We make a lot of videos. We actually made a couple this week that will be premiering over the next 2 weeks. So follow us on YouTube, subscribe to our channel. You can follow us on Facebook, on Instagram, and on Twitter. Also follow the Gemini Observatory and Noir Lab, where Jamaica works, to find out all about the exciting science they do there. If you are on the Big Island, I highly encourage you to come to our Waimea Science Walk. Our Waimea Science Walk is brought to you by the Mauna Kea Observatories, Canada, France, Hawaii Telescope, and the Keck Observatory, along with a variety of other scientific organizations on island. The idea behind the Hawaii Science Walk is we want to promote all of the incredible science that's being done on Hawaii Island. And so we worked with the the National Humpback Whale Marine Sanctuary, the Hawaii Wildlife Center, the A'ala Project, the Volcano Observatory and the National Park Service and the National USGS, the Mauna Loa Observatory and NOAA, the Daniel K. Inouye Solar Telescope, the UH Institute for Astronomy, and the Keck Observatory. Everybody made a video going from the center, from the depths of the ocean all the way up to the cosmos, and the question about biomarkers and life in the universe, and how all of the scientific research done here on Hawaii Island and across the state, how all of that information goes towards astronomers answering these really big questions like, are we alone? So we will put the link in the chat here for the Hawaii Science Walk page. If you don't live in Waimea and can't do the physical walk along Ala Ohia Street, you can download the coloring sheets from our Hawaii Science Walk website, along with the go and watch the YouTube channel for the Maunakea Observatory's YouTube channel. We have the Maunakea Observatories have a YouTube channel as well. Every Monday, we air content as part of our MKO at Home that started at the beginning of the pandemic. Over the next couple of weeks, we are going to be airing these Hawaii Science Walk videos. You can also go to the CFHT Star Party website, which probably many of you got to here, and look at all of the videos that we created for the Star Party this year and in years prior. We also have the Waimea Solar System Walk. Again, it was a walk that was done socially distanced and self-guided, where you could walk down Ala Ohia Street and get a feeling for the scale of our solar system. Those videos are available on YouTube. You can also go to our website and get more information. Those videos are both in English and Avelo Hawaii. So it looks like that looks like a Jupiter. Yay, let's give all of Jamaica a round of applause. Woo-hoo, Jamaica.
I appreciate that. It's still, so now it's not too bright. That's great. And we don't have the hairs coming off of it. That's awesome. But we want to see more finer details. So I'm gonna, if you guys will bear with me for a few more minutes, I'm gonna see if I can tweak this a little bit more. And this is definitely always an experience and work in progress. I'm definitely learning as I go all the time, for sure. So I'm going to try the focus here. And while Mary Beth was talking just now, I thought I almost had it. I was excited, and then it didn't happen. So let me get back here right now, move it back up.
You're getting some shout outs in the chat. Jamaica Mojo says, great job and stay warm. Jasmine's wondering, do we have a moon transiting? Well, that's something we can Google. Not you. That was not shade on you, Jazz, that you could Google it. We can Google it and get you that answer.
That's a great question, Jasmine. And again, Jasmine, thank you so much for the help and suggestions. Mojo, thank you. I appreciate the support and feedback, and I am staying pretty warm. Thank you. All right. Well, I'm going to move Jupiter back up and see if we can get a little bit more detail. And yes, I do think there are a few, at least one moon transiting. And one of the reasons I love looking at Jupiter is because it really is a solar system in microcosm, because over a couple of hours, you can see the Galilean moons really transit and go around. I'm going to stop real quick and move Jupiter back up and see if I can get some fine tuning real quick, Mary Beth.
Right, and I am answering Jazz's question. Presumably. Oh, this only goes to August. right. Okay, so how are people with universal time?
Oh, that's interesting. Universal time.
I say that because it looks like both Ganymede, Io, and Europa are all transiting today at different times UT. So that's universal time. So that's Greenwich Mean. So what, Callie, that's 10 hours ahead of where we are now. So nope, Io is, at this moment in time, Io is being occulted by Jupiter, which means that Jupiter's here and Io is behind it, so we can no longer see there. So it doesn't look like there are any transits at the moment. So those must be the artifacts. And an image artifact is just, you know, it's a place on the image where maybe there was something that was warm and made a hot pixel, so those electrons never settled back down, or it could be a distortion or something, you know, physically on Jamaica's CCD, or like the lens. We once had a moth get stuck in Espinons. We didn't actually lose any light, and the moth was dead, but hey, these things happen. A lot of questions about that moth.
I bet there were. Okay, so I am a few more things here. All right, I'm gonna move Jupiter back up. As you can see, it's gone. I'm just making some changes here to see if I can get that image a little bit better. It's so bright. All right. And I heard you talk about your favorite planet and favorite objects in the night sky. Jupiter is definitely one of mine, for sure. I love being able to show the moons going around. So I'm really bummed that I haven't quite gotten it yet. All right, so I'm gonna try this one more time, move this up, and then let's round out. I'll go ahead and move to Saturn because at least I'm glad we've been able to see the things and attempting to do things, which has been awesome. So let me move up Jupiter. Next we'll hit Saturn, and then we'll talk about how, well, all the outer planets actually have rings. We think of Saturn as the Lord of the Rings, but in fact, all the outer planets have rings. So I'm going to mute myself and work on Jupiter for another moment, and then I will drop in the chat when I transition to trying to get Saturn.
All right. So as Jamaica mentioned, all of the outer planets have rings. And so the rings of Jupiter, though, are really dark. I used a word when we talked about Venus called albedo, and that's a measure of the shininess of an object in space. Well, I guess albedo is the measure of a shininess of an object, regardless of where it is, but we're talking about ones in space. So the albedo, the brightness of Jupiter's moons is really low. In fact, for a long time, astronomers weren't even able to detect them. That's because those, the pieces of rock that are surrounding and making the ring, and that's what rings are made out of. Rings are not solid like this. You can't like walk across the ring. The rings are made of pieces of ice and rock and dirt and dust and chunks of gases that the sunlight shines on. And so depending on the composition, the object can get as the sunlight hits it, it can melt a little bit. And so sometimes you can get almost like a carbon shell on the outside of it. And so that makes it very dark. Think of like a graphite in a pencil versus a diamond. So we're not talking about sparkles like a diamond. We're talking about sort of that darker kind of carbon charcoal kind of color. And that prevents us from being able to detect those in optical light, like that your eyes can see. And depending on the temperature, it can be even tricky in the infrared. So Saturn, Jupiter, Uranus, and Neptune all have rings. Neptune's rings are, Uranus's rings are actually fairly bright in the ultraviolet. And so if you look at one of my favorite pictures of Uranus is actually a picture of the Uranus ring systems, which instead of going around the equator, actually go in this direction around. They go around the equator of Uranus, but if you recall, I said it's a tipped over planet. So instead of the rings of Uranus going this way, they go this way. But Saturn has the most famous rings. And one of the reasons for that is that one of the moons of Saturn is very close to the edge of Saturn's rings, and it is also volcanic. And so as those gravitational forces cause that moon to the volcanoes on that moon to erupt, those pieces that are erupted from the volcano end up orbiting and forming a new ring layer on the outside, which is good because the inner rings of Saturn likely fall to the surface of the planet. And this is actually a scientific discovery that was made several years ago, I believe, by the Gemini Observatory, that as these rings spiral inward, they actually rain down on the planet, adding warmth. And so you can actually see where the rings are falling in the infrared. In the infrared. Now, we can imagine a naked Saturn. So if we look at Saturn without its rings, you'll notice that it has striping very similar to Jupiter, but just not as bright. And that's because not as distinct. That's because the same processes that we see on Jupiter exist within Saturn. Saturn being a slightly smaller planet than Jupiter, those convections and the rising and falling, it's just not as extreme and pronounced. And there's also potentially less of those coloring agents, like I mentioned, methane and ammonia, that change the color of Saturn. So Jamaica is slewing to Saturn now, and I'm going to take this as an opportunity to talk about the only planet in the outer solar system that I've not mentioned, Neptune. So Neptune is the planet farthest from the sun. It is blue. When we think about planets, we often put them in two categories, right? You've got the terrestrial planets, the Jovian planets, planets like the Earth, planets like Jupiter. I actually like to do a third category, and those are the ice giants. So Saturn and Jupiter have a lot in common when it comes to composition. Lots of hydrogen, lots of helium. But when we look at Uranus and Neptune, they have far more methane, they have ammonia, they've got other hydrocarbons. They almost have like a windshield wiper type chemical formula. And so those planets are fundamentally different in composition than Jupiter and Saturn, but they just happen to be larger. Now, when we say ice, people often think water ice, but I want you to think of like frozen carbon dioxide. And, I keep saying methane and ammonia, but those guys, that's really what we're looking at when we refer to as those ices on those two planets. So they're blue, again, because of those colors. Uranus is a paler blue. Neptune tends to be a little bit more of an intense blue. Uranus and Neptune both likely rain diamonds in their interior. And because their atmospheres are so rich with carbon, as we see those convections, that rising and flowing, what happens is as the material cools, it goes down towards the center of the planet. We get more heat and more pressure, which causes the carbon to precipitate, to fall out of those molecules. And carbon under intense heat and pressure form diamonds. So it's raining diamonds. Before anybody has the idea of every fourth grader of getting a giant net and just kind of scooping it up, Those, by the time the diamonds would hit anything that would even come close to a solid core, they have been crushed under the extreme heat and pressure. That carbon is released into the atmosphere, rises, bonds again with the other elements, goes up, and just this whole cycle. So similarly to the water cycle that we have on Earth, astronomers hypothesize that there's a carbon cycle on Uranus and Neptune. So it looks like Jamika is in the process of slewing to Saturn. She's giving us the thumbs up, guys. She's slewing to Saturn.
Yes, I am. Saturn happens to be, it's actually not low if we were at sea level, but we have some poo-oos here right across the road. That's it's pretty low, and I have the wall right here. So I'm kind of catching part of the wall, but I'm gonna retry here in just a moment.
All right, so we've got about 10 minutes left in our broadcast. Does anybody have any questions for these last couple of minutes here while we wait for Jamika to slew to Saturn and to find it in the telescope?
And one thing, if there's not a question about this yet, is the change in angle of Saturn and when those rings will tilt to be edge on and appear to actually not be a planet with rings anymore.
So I will answer that. So as Saturn orbits around the sun, you know, all of the planets in the solar system, the Earth included, are tipped over. So they have some sort of, they're not directly straight up and down. They have some sort of tilts to them. So as Saturn orbits around the sun, we see it in different positions. Sometimes we'll actually see it kind of edge on like this, where we can see Saturn and then a gap. Other times we see it as the way Galileo did with ears. And then other times, if we're seeing it, you know, kind of a straight on or at another angle, we end up not seeing the rings at all. So I've seen Saturn in a variety. You can see it kind of tilted, half tilted. This is the coolest because this looks like this. It's also pretty awesome when you can kind of see the ears. Saturn is one of those things that I absolutely love to look at in a telescope because it looks like what you want it to look like. You know, if you would pull up, you know, go to say the Orion Nebula with Jamika's telescope right now, and you compare that to, you know, the CFHT picture of the Orion Nebula that we have, they're not the same. They don't look the same. When without filters, to be able to differentiate between the colors, when your eye sees a whole bunch of color at once, it makes it white. So you look at the Orion Nebula, you might see a little hint of blue, but it's going to look predominantly white. Saturn looks exactly the way that it is supposed to look. And here's a really great example that Callie gave me of what that would look like in optical light. And so what you would kind of expect it to look like through a telescope is not going to be through a small telescope. It's not going to look like this. This is probably 21 different images. We had blue light, we had red light, we had a yellowish green light. And when those images read off the telescope, when we see them, we're actually able to add color to them. Now, Jamika just messaged me that it turns out that Saturn is too low, but fear not, I have a picture of Saturn that was actually taken by CFHT, by our instrument Spiru. So this was the guider of Spiru. So this means that we weren't taking a spectrum, we were just taking, trying to find a specific spot. And here you'll notice we can see this is in the infrared. So again, heat and space. We see exactly where we would expect to see this banding. This area is going to be a different temperature than the area above or below it. We can see the really nice gaps in these rings. There's actually these little moons called shepherd moons. And these shepherd moons They exist with inside the rings and inside of this, I believe this is the Huygens gap, inside of this gap. And the gravity of these little moons keep the rings in the form that we see. So we can see that the inner rings are warmer. That shouldn't be a surprise now that we've talked so much about gravity and gravitational heating and tidal forces. They're likely warming up the particles that are closer as opposed to the particles that are a little bit farther away. So with that, we've just got a couple minutes left here. I think we should give Jamika a round of applause for all of her attempts tonight at getting us really nice targets on the sky. Does anybody have any last questions or anything, Jamika, that you want to say before we decide to call it a night?
Well, I have decided to turn the telescope around and look to the back here. Of course, you mentioned the Orion Nebula. It's just coming up above the VIS building. I thought I would try that, or the Pleiades, in these last 6 minutes.
All right.
I will do that right now.
Give it a whirl. So we've talked about the Pleiades. I alluded to the Orion Nebula just a moment ago. So let me bring that picture back up and we can take a look at that. I'm actually going to show you the Orion Nebula first. We saw the optical light our eyes can see. Let's actually for a moment now go to infrared, light that our eyes cannot see. And we can see the difference there between the two. So we're actually going to go to the Maunakea that I mentioned, but I'm still going to show you the Orion Nebula. The Maunakea, the little eyes, as it's known in Hawaiian, which is the Pleiades. So if I can do this real quick, I'm going to show you. So we saw the Orion Nebula a moment ago looking like this, really bright. All of this gas completely lit up. Well, the thing about that gas is that it's actually very cold, making it transparent in the infrared. So we're able to see through all of those clouds of gas and dust that are being illuminated by the stars inside to see the stars inside that are causing that illumination. And so I am actually going to put Callie on the spot and see if she can find us an image of the Pleiades, which is on the 2021 calendar. Callie and I clearly work together a lot because I didn't even ask and she brought this. I was in the process of asking and she had already found it for me. We spent a lot of time together.
I was going to say also the CFHT calendar being here at the VIS used to be something that was stocked here all the time, and it has just amazing. Some of the images she was showing, it's absolutely amazing. So if you happen to be on Big Island and you do come to the VIS when they're open, are the CFHT calendars now in stock here?
They will be soon.
Awesome. All
right. So here's the cover of our 2021 calendar, and this is the Pleiades, the Maunakea. And the brightest stars that we see here are the stars that we would see with our naked eyes if we were to go out. You notice there's a lot of blue kind of surrounding them, and that's going to be, as I mentioned, these are very hot, very new baby stars basically, and so they still have some dust that's surrounding them, and the light from these really bright stars is illuminating that dust, giving these the nebulosity that is surrounding them. So nebulosity is the fancy way of saying they're surrounded by a nebula. I really like them because I like the color blue. And I just love how this is just like all like glowing and pretty and blue. For me, this really makes me think like holidays, like a real nice kind of holiday season vibe. So this is what Jamika is going to try and find us. Now, keep in mind when she does, it is not going to look like this. This is again 21 images taken under excellent conditions. The color, it's a true color. So the parts that you see are blue represent the blue portion of the electromagnetic spectrum. But Jean-Charles Couillon, who creates our calendars for us, he picks the shade of blue, makes the blacks a little bit blacker, and does the kind of art part of that really optimizes it both scientifically, but also aesthetically pleasing. So it looks pretty. All right, Jasmine has an Orion image that she took. Waiting to see, I think she's probably, I'm guessing, uploading that. Thanks, Jazz. All right, I want to thank you all so much while Jamika is continuing to do this. I'm going to do my thank yous. Thank you all so much for tuning in and staying with us. I don't know how many of you have been here since 6:30, but if you have, mahalo for sticking with us this evening. If you've joined us late, I'll just reintroduce myself. I'm Mary Beth Lachak, Director of Strategic Communications at the Canada-France-Hawaii Telescope. I am accompanied by the always fabulous Jamika Marshall from the Gemini Observatory, which is part of Noir Lab. Jamika is braving the probably in the 30s Fahrenheit temperatures of the Visitor Information Station for us at 9,000 feet. Our technical support this evening is Callie Crowder, who is one of my coworkers. If you have seen a CFHT video, Callie is the director. We co-produce, and she refers to me as the on-air talent, which I can't believe I told you because is awkward. So Callie has been handling the back end. She has set up the link. She is making sure that everything works smoothly. And she is the one who is in charge of the live streaming. This has been recorded. So if you tuned in early or tuned in late or needed to leave early and you want to catch the entire thing, or you're like, wow, this is so fantastic, I'm going to tell everyone I know that they should spend 2.5 hours with Mary Beth, Callie, and Jamika, please do. We'll post the link on our social media. If you don't follow us on social media, please do. At CFHT Telescope on Instagram and Twitter, and at Canada, I think we're also at CFHT Telescope on Facebook. You can also, you're all on our YouTube channel right now, click subscribe, and you will see when our new videos come out. We will have one video this week, one video the following week. This week we're talking about asteroids. Just a little bit of a teaser. I throw a pine cone really hard with much more force than I anticipated on the sidewalk to explain how asteroids, the difference between an asteroid, a meteor, and a meteorite. That video also has some really snazzy work by Callie on animations. Next week, we'll have, in celebration of the winter solstice, our What is a Solstice video. So I see Jamika is tinkering and tinkering and tinkering.
I actually came over here. You were talking about the Orion Nebula. I thought the edge of it is just above the VIS now. So I'm just trying to get that on screen as we round out. I see we're a minute over, but I almost have it. Is that okay?
Yes.
All right, awesome. And then I would like to say thank you to Callie, to everyone for all of the support and feedback and just opportunity to hone our craft and also to share science and to all of our passion and excitement about the things that we do with the public. So I'm going to stop right now and put my other hand back on the control panel because I know I want to be closer so you can hear me. Pop back over here real quick, Mary Beth, and thank you all again for joining us in the audience. All right,
So let's end with the Orion Nebula. Fingers crossed. This is it can be a little bit tricky if it's coming over the edge of the VIS.
Yeah, it is, and it's not very bright right now because the moon is out, so it's right there. Okay. try that one more time. Don't want that. Okay. All right, there we go. Try that. Okay, I'm still getting the red light from. I don't think I'm going to be able to pull that one out, even to just get a slight look at that one.
That's okay, Jamika. I think it's time that you go inside, see if the Vizzle gave you some cocoa. And mahalo everybody for joining us. Thank you so much, Jamika, for braving these conditions for us. I know that when we have winds that are the speed that you're having there, I wouldn't be surprised if we're having a little bit of wiggle in the telescope as well. So this has been challenging observing for Jamika, and she rocked it for us. So mahalo everybody for joining us. Have a wonderful holiday season, and we look forward to seeing you in person or virtually. Mahalo, goodbye, and aloha.
Mahalo, aloha.